All right, so for problems 1 through 4, we're going to select two numbers randomly from this set 1, 2, 3, 4, 5. So we want to find the probability that both numbers are even. So, you always want to be very clear about what your sample space is. So in this particular problem, our sample space S is 1, 2, 3, 4, 5. Now, how about the number in this sample space? So that's 5, right? Notice the difference in notation. Now, to find probability, you need to know the number of the event divided by the number in the sample space. That's pretty much how you find probability, although it's not always just so simple to calculate those things. But the number in the sample space is pretty clear. There are 5 in the sample space. But the problem is we're selecting two numbers randomly. So not just one number, but two numbers. So if we're selecting two numbers, then our sample space is not going to be 5 because we're selecting 2 at a time, right? So it would be the event out of 5 if we were just selecting one thing. But since we're selecting two things, it makes it slightly more complicated. So let's think about this. How could we do that? So if we were going to select two things, first let's talk about it in terms of permutation combination. Then we'll look at it a completely separate way. But does the order that we select these two things matter? Okay. It doesn't say anything about the order mattering. You're just selecting two numbers. You could select them even at the same time. So I would say the order does not matter when we're doing this. And so to figure out the sample space, and the bottom, the number in the sample space, if we're selecting 2, how many different ways could we select 2? Now again, think about it. You can select a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 2 and a 1, a 2. You see what I mean? But a 2 and a 1 and a 1 and 2 is the same. But if the order doesn't matter, that's a combination. Now, how many are we selecting? We're selecting 2. Remember, that's the number that goes on the right. How many are selecting it from? 5. So it's really a combination of 5, choose 2. Okay? In the numerator, our event is we're selecting even numbers. So we need to take a look at what of those numbers is even. Well, 2 is even, and I'm highlighting it, and 4 is even. And it's highlighted there. So how many even numbers do we have to select from? Well, 2. How many of them need to be even? Well, it says both numbers are even. So that's 2, choose 2. Now, if we run this calculation, remember, you could type that in your calculator. It's fine. Or if you use the formula, that's 2 factorial divided by the same 2 factorial times 2 minus 2 factorial. Now, 2 minus 2 factorial is 0 factorial, which is 1. And these 2 factorials cancel. So that's 1 over 0 factorial, which we already said that's 1. So the numerator is 1. Divided by 5 choose 2. Again, that's 5 factorial divided by 2 factorial times 5 minus 2 factorial. Okay? 5 factorial over 2 factorial. 5 minus 2 is 3 factorial. Parentheses not required there. And then you write the top one down to match the bottom one. So it's 5 times 4 times 3 factorial. Divided by 2 factorial is 2 times 1. But this 3 factorial is going to cancel, which gives you 5 times 4 is 20 divided by 2, which is 10. So that gives you 1/10. All right. Now, there's another way to handle this. To me, it's a little bit easier, but it just kind of depends on how your brain's working at the time. Let's select the first even number. Okay. Now, how many do we have to choose from? Well, we have 2 even numbers to choose from out of 5 for our first draw. In our second draw, if we drew an even number, we have 1 to choose from out of 4. If I multiply 2 times 1 is 2, 5 times 4 is 20, and I reduce that, that's the same 1/10. It just really depends on how you think about it, right? You could use combinations because the order doesn't matter, or you can think about the multiplication principle and choose the first random number and the second random number. For problem 2, we're talking about both numbers are prime this time instead of even. So let's take a look at our prime numbers. Now, 1 even though the factors of 1 are 1 in itself, so that kind of meets the definition of a prime number, but 1's not considered a prime number. 2 is the smallest prime number. So 2 is prime, 3 is prime, and 5 is a prime number when you're thinking about this. So if I think about it in terms of combinations, the event of getting a prime number is a combination of, we have 3 prime numbers, we're picking 2 of them, okay, and then what is our total sample space? Well, we're just randomly taking a set of 5 numbers and picking 2 of them. And on the previous page, we already calculated 5 choose 2. Let me go back and find that. So 5 choose 2 was 10. Let's keep that in mind when we're doing this problem. So we have 10. Oops. So my pen is not cooperating. There we go. So 5 choose 2 is 10 in the denominator, but what's 3 choose 2? Okay. Definition, that's 3 factorial over 2 factorial times 3 minus 2 factorial. So that's going to be 3 factorial over 2 factorial times 1 factorial. 1 factorial is just 1 over 10. And 3 factorial, we can write it down as a 3 times 2 factorial over that 2 factorial. And basically, you just get 3. So the answer is 3 out of 10. Now, could we do this the second way we did the other one? By taking a look at just selecting the numbers. Like our first pull out of the pile up here, we have 3 to choose from out of 5. Now, if the first is a prime number, now we have 2 out of 4 to choose from. That would give me 12 out of 20. Hey, let me try it again. That's not 12, is it? How about 6 out of 20? 3 times 2 is 6, y'all. And then divide each of these by 2. So that would be 3 out of 10. See, it works that way as well. Again, the blue way to me is a little bit easier to understand, but you still have to understand commutations and permutations, so I like showing you both ways. Question 3, we're still drawing 2 numbers from our list of 1 through 5, and this time they want the sum of the 2 numbers is odd. Then you might start thinking, wait a minute, so sum means I'm supposed to add these numbers together, and then I've got to think about, you know, if I add 2 odds, I get an even, or if I add an even and an odd, I get an odd. You might start thinking of all those things, but it should remind you of the dice. Remember, we do the sum of die? So, consider across the top, you know, you have choices of 1, 2, 3, 4, and 5. And then down the side for your second choice. Like that, right? And you could have a 1 plus 1, which is 2. But can you get a 1 and a 1? Notice it says without replacement. So 1, 1 is not an option, but 1 plus 2 is 3. I'm going to go ahead and put the sum there. 1 plus 3 is 4. 1 plus 4 is 5, and 1 plus 5 is 6. Next row, 2 plus 1 is 3. 2 plus 2 is out of the picture. Why? Because you can't get 2 2s, because again, when you randomly select a number, you can't put it back and select the second one. I mean, picture picking the numbers at the same time. You're going to pick a 2 and a 3. You can't pick a 2 and a 2. 2 plus 3 is 5. 2 plus 4, let me make this clear. Here we go. So I'm on row 2, lined up with the 4, I'm adding them together to get 6. Row 2, lined up with the 5, I'm adding them together to get 7. See what I'm doing? And then 3 plus 1 is 4. 3 plus 2 is 6. But 5, I can't add today. 3 plus 3 is 6, but I can't get a 3 and a 3. 3 plus 4 is 7. 3 plus 5 is 8. 4 plus 1 is 5. 4 plus 2 is 6. 4 plus 3 is 7. 4 plus 4, I'm not allowed to do because it's 2 4s. 4 plus 5 is 9. Last row. 5 plus 1 is 6. 5 plus 2 is 7. 5 plus 3 is 8. 5 plus 4 is 9. 5 plus 5 is 10, but that's out of the picture. So let's do this. It's asking for the sum is odd. So look, 3 is an odd number. Ooh, I need to make that bigger, don't I? 3 is an odd number, 5 is an odd number, 3 is odd, 5 is odd, 7 is odd, 5 is odd, 7 is odd, 5, 7, 9, and then 7 and 9. I think I've got all the odd ones highlighted, right? Now, how many do I have highlighted? That's my event. So again, remind me, how many do I have highlighted? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, it's like 12 of them. Out of the total, I don't even know how many is in my sample space, right? I need to count all the sums, not the dashes, because they don't count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 possibilities. Now, we simplify that. 12 out of 20 reduces to, well, 2 divides into both of them, 4 divides into both of them. 4 to 12 goes 3 times, 4 to 20 goes 5 times. So 3 out of 5 should be our answer there. Okay, so we still have the numbers 1, 2, 3, 4, 5. This time it says the product of the two numbers is odd. Now what does product mean? Multiply, yes. And so I have to multiply these things together every way possible. Okay, so again, let's make a list of our numbers. 1, 2, 3, 4, 5. And down the side also, 1, 2, 3, 4, 5. And we're going to make a product table this time. So 1 and 1 is out because this is, again, without replacement. So I grab a number and I grab another number. Okay. 1 and 2 is a possibility. I multiply those together and get a 2. 1 times 3 is 3. 1 times 4 is 4. And 1 times 5 is 5. 2 times 1, that's a possibility also, right, is 2. 2 times 2 is out. Can't do that because, again, if I draw the 2, I can't put it back in the pile and draw the 2 again. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is not a possibility because when I pull out that 3, I can't pull out a 3 again because I've already pulled it out. 3 times 4 is 12. 3 times 5 is 15. Almost there. 4 times 1 is 4. 4 times 2 is 8. 4 times 3 is 12. 4 times 4 is 16. And 4 times 5 is 20. But what did I do? I messed up. 16 is not possible. I got carried away with my multiplication. 5 times 1 is 5. 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. But 5 times 5 is not a possibility because I can't draw 5 and then draw 5 again. Now it asks us the product odd. Okay, so let's highlight the outcomes where the product, I don't know what just happened to my screen there, is odd. We can do that. So 2 is not odd, 3 is an odd number, 5 is an odd number, none on that row are odd, 3 is odd, 15 is an odd number, none on row 4 are odd, and then finally on row 5, 5 is an odd number, 15 is an odd number. So if we count those outcomes, go 1, 2, 3, 4, 5, 6 of those out of how many possible outcomes? Well, just like before, if you count all the possibilities, there are 20. And 6 divided by 20, or 6 reduced to lowest terms, is going to give me 3/10 is the final answer for number 4. Okay, so for the next problem, for 5 through 7, the manager of a pizza parlor, which operates 7 days a week, allows each of 3 employees to select 1 day off next week. Assuming the selection is done randomly, which means they're not picking a preference, you just randomly pick a day off out of the 7. And independently basically means that one person's selection is not going to affect another person's selection. Find the probability of each event. So for number 5, the event is all 3 employees select different days. Now let's think about how that could happen. Now let's one employee at a time. So the first employee has 7 days to choose from. How many can she pick? Well, there's 7 possibilities for her 7 days to choose from. But now if we want all employees to have 3 different days, the next employee has 7 to choose from still, but 1 day has already been picked. So there's 6 available if all 3 have different days. And finally, the last employee also had 7 days to choose from. So 7 times 7 times 7 at the bottom is all the possibilities. Nobody said they couldn't reuse days. They could all ask for Monday off. But we want to know how many of the outcomes happen to be 3 distinct days that are different. So the third could have 5 days since 2 days have already been selected. And you multiply this out, and you could simplify a little bit beforehand, but your calculator will get you there too. Look, that 7 can cancel with that 7. And what we get is in the numerator, I have 30. And in the denominator, 7 times 7 is 49. And I don't see any common factors there, so that would be lowest terms. Okay, for question 6, all 3 employees select the same day. Given that, remember that reduces our sample space. So whenever you have a given that, you have to reduce your sample space to all 3 select a day beginning with the same letter. And this is really just a think it all the way out kind of problem. So one possibility of them all selecting a day beginning with the same letter. What if every one of them picked a Monday? Okay, so Monday, and you could say employee 1, 2, and 3 picked Monday. That'd be true for Tuesday too. That's one of the possibilities, right? Wednesday. And this could be all 7 days of the week. Okay, so Thursday, they could all pick the same day. Friday, they could all pick the same day. And these 1, 2, and 3 that I'm circling, that's just your employees. Saturday, they could all pick the same day. And Sunday, I'm going to write that out a little bit better, they could all pick the same day. Okay? But now, that's not it, because we've got this given that, see, all of these, given that all 3 select a day beginning with the same letter. So in this case, they all pick the same letter to start with, which is an M. All these picked a T, all these picked a W. But that's not the only option. Because what about Tuesday and Thursday? They start with the same letter, right? So what could happen is number 1 could pick Tuesday, right? And then 2 and 3. Ooh, I want to make that smaller. I'm using the blue to denote Thursday to keep this organized. Okay, so 2 and 3 pick Thursday. Or 2 picks Tuesday, and 1 and 3 pick Thursday. Or 3 picks Tuesday, and 2 and 1, I did that out of order, picks Thursday. So in that case, one of them picked Tuesday and 2 of them picked Thursday, but we could flip that around also, right? Can't 2 of them pick Tuesday and 1 of them pick Thursday? So let's try that. So 1 and 2 pick Tuesday, and then number 3 picks Thursday. Or 1 and 3 pick Tuesday, and 2 picks Thursday. Or 2 and 3 pick Tuesday, and 1 picks Thursday. Now, that's every way that I can imagine doing that, where you have Tuesday and Thursday. Or they all pick Tuesday and they all pick Thursday, and we have that listed over here. Now, that's not the only situation. We got Saturday and Sunday going on too, right? So Saturday and Sunday, now do you agree it would look just like this? Now, I won't write out the options for Sunday, but all of those options could still happen on Sunday. And what I mean by that is it's the same list, except green would be Saturday and blue would be Sunday, that kind of thing. Now what matters is, let me change colors here. Notice there are 6 of these. There would be 6 of those if I wrote them out. How many of these do we have? Well, 7, right? Because it's 7 days a week. So whenever you do a given that problem, remember the denominator is how many meet that criteria, the given that. And the given that is all 3 select a day beginning with the same letter. That's what we were listing. Every possibility when all 3 employees could pick a day starting with the same letter. Well, there's 19 of them. 7 plus 6 plus 6. But now, what goes in the numerator is all 3 select the same day. Now, how many of all those 19 do we have listed where they're all the same day? Well, that's this first list over here. Like all 3 employees pick Monday, and all 3 employees pick Tuesday, and all 3 employees pick Wednesday. So that's 7 out of the 19 possibilities where if they all pick the same letter day, that they would happen to be the same day. It's a strange problem. All right, for example, or question 7, it says exactly 2 of the employees select the same day. Now, as you figured this out already, I'm sure there's more than one way to get a problem done. And I noticed that I attempted to do this one way, yet the book solution was a different way. I'm going to show you both. First, I'm going to show you the way that I thought about it. Exactly 2 of them select the same day. So, for example, employee 1, employee 2 could select the same day. Or, employee 1 and employee 3 could select the same day. Or, employee 2 and employee 3 could select the same day. Okay? Now, there's no math involved here. I'm just thinking this through. Now, if employee 1 and 2 select the same day, employee 3 would have to select a different day, right? Because it says exactly 2 of them. Not at least 2, not at most 2, but exactly 2 of them. So the first employee, she'd pick any day, or he could pick any day he wanted. So that's 7 out of 7. The next employee would be 1 out of 7. Why? Because the day is already picked. Okay, so there were 7 days for each employee to pick from. And the first one picked a day, and the next one's exactly the same day. Now, the third employee had to pick a different day. Am I right? So that means there's 6 days left out of 7. What does or mean? Add. Remember, or in terms of probability means add, and means multiply. So let's do this again. Employee 1, there's 7 days for that employee to pick from. Employee 3 picks the same day as employee 1 did, so there's only 1 day out of the 7 to pick from. But employee 2 over here has to get a different day because exactly 2 of them are picking the same day. So that's 6 out of 7, right? And these things are ands because employee 1 and employee 2 and employee 3 are selecting days. Or, again, means add. So employee 2 has 7 days to pick from out of 7, but employee 3 matches employee 2, right? So that's 1 out of 7 days, and I didn't write over here, but it was employee 2 that has to pick a different day there. It's employee 1 that has to pick a different day, and there's 6 out of 7. And notice this is all the same value for all of these. And I just kind of calculated it by hand because I noticed that, look, this 7 cancels with that 7, and that gives me, back to green, 6 out of 49, plus the same thing happens, 7 and 7 here, 6 out of 49, plus 7 and 7, 6 out of 49. When I add those together, that 6 plus 6 plus 6 is 18 out of 49. That's the way I calculated the probability. So then I always try to go check my answers in the book, because probability can be very confusing and easy to miss problems, just like the counting chapter that we did. And they handled this differently. They stated that exactly 2, okay, is the complement of, what is exactly the complement of? Well, exactly 2 is the complement of all 3 pick the same day, and none pick the same day. So let's calculate those values. So all 3 pick the same day. Let's calculate that. So that means the first person picks a day, and they can pick anything they want, but the next person has to pick the same day. So that was 1 out of 7, similar to what we just did. And the third person also picks the same day. That's 1 out of 7. Now, happens to be, just like before, this 7 cancels with that 7. Or just type it in your calculator. And I get 1 over 49. Now, none of them pick the same day. This is convenient. We've already calculated that. Let me go back, and that was problem. I'm going to change the screen on you. That's right here. All 3 select different days. That was question number 5, 30 out of 49. So I'm just going to recopy that. So this was 30 out of 49. That was, again, question number 9. Now, what do you do when you find the complement? You do 1 minus. So 1 minus, that's all 3 pick the same day, which is 1 over 49, or none of them pick the same day. So I have to add 30 over 49. And remember, you have to do this parentheses stuff first. So this is 1 minus. That's 31 over 49. Now, when I find a common denominator, I have to change this 1 to 49 over 49 minus 31 over 49. 49 subtract 31 does give me 18 over 49. I guess the pink one, the way the book did it, is a little more efficient, but it was just not, it's not what came to me first. I just calculated the probability that exactly 2 of them select the same day. And the only ways those can happen, if 1 and 2 select the same day, or 1 and 3 select the same day, or 2 and 3, and I just calculated all that separately. Again, notice the or statements mean add, but the and means multiply. And this was definitely a challenging problem. Okay, so problems 8 through 10, it says the chart represents genetic transmission of cystic fibrosis. Capital C denotes a normal gene, and lowercase c denotes a cystic fibrosis gene. And notice it says the normal is dominant. That's why it's capitalized. Both parents in this case are CC, which means that they inherited one of each gene. Therefore, they are both carriers but do not have the gene. So remember, when you have a capital letter that's dominant, that's the outcome of the child. But you're still a carrier because it's the lowercase. So what we have is a parent that is normal, because normal is dominant, but is a carrier of cystic fibrosis. Same thing with the second parent. Now, number 8 says complete the chart showing all 4 equally likely gene arrangements. So remember, you're just filling in the table. So we have a row and we have a column. And on the first row and the first column, they're both capitalized. So that's capital C, capital C. Now, the first row, second column is already filled in for us, which is capital C, lowercase c. Now, the second row, first column, notice it's a lowercase c, but the second parent is capitalized. And then for the last situation, again, the first parent's a lower c, and the second parent's a lower c. C's are not my favorite letter for this because a lower c looks like an upper c. But there we go. So notice this first option here, those are both capitalized C's. The second one that they did for us is a capital C, lower c. This third one, bottom left, is a lower c, capital C. And then the fourth one is lower c, lower c. Okay, so that answers question 8. Question 9, find the probability that a child of these parents will also be a carrier without the disease. So let's highlight a carrier without the disease. So remember, a carrier without the disease is just like the parents. So you have a capital C and a lower c. That happens in this situation and in this situation. Okay, so notice there are 2 of them. The one I didn't highlight, the capital C, that's a normal child that's not a carrier. Lower c, that's a cystic fibrosis situation there. So the only 2 that meet the criteria for number 9, again, the 2 that I have highlighted, and that is 2 outcomes out of the 4, which reduces to 1/2. So that would be the answer to number 9, is 1/2. And number 10, what are the odds that a child with these parents actually will have cystic fibrosis? That's the 2 lower C's, because there's no dominant capital C in there. So it is this single situation here that fits number 10, and that's 1 out of the 4 equally likely outcomes. So 1/4 is the answer to number 10. If you have questions about 11 on, go ahead and check out part 2, possibly part 3 videos. Hey, don't go yet. Guess what? I didn't answer the question correctly on number 10. It says, what are the odds? Not what is the probability, but what are the odds the child with these parents actually will have cystic fibrosis. So that's for and against. So we're talking for cystic fibrosis. That's 1. How many are not cystic fibrosis? That's 3. So I'm going to learn like you. We got to read the directions. Whether does it ask for probability or does it ask for odds? This one asks for odds. So this is the probability over here. Probability of CC is 1/4, but this is the odds, and that's what I was supposed to answer. Now, we're going to call it and come back on a part 2 video.